Okay, so let's have a look at the combination of transformations. And as I mentioned, there are a couple of ways we can approach them. Let's firstly consider just the coordinate approach. Okay, so if we want to find the rule for the image applied, obviously there's our function there, y equals x squared plus 1. Now, dilate from the x-axis by a factor of 4. If we're going to move from the x-axis, the y value gets affected 4 times, 4y. Reflect about the y, y-axis means the x value gets affected. The x value swaps signs, so negative x 4y. Translate 2 units to the right, we add 2 units to the x value, 3 units down, I take away 3 units from the y value. So what we're saying, the new x value and the new y value is equal to negative x plus 2 and 4y minus 3. So I guess the key is to remember that our equation is given in terms of old y and old x. So we want to rearrange to get what they are equal to. So if we equate the coordinates, we know that x dash is equal to negative x plus 2, y dash is equal to 4y minus 3. Transpose those equations, I get x equal to and y equal to. And then once I've done that, I can substitute those values into whichever rule I've been given. So it doesn't matter whether it's x squared plus 1, e to the x, you know what I mean? You just substitute that in for the corresponding x and y value. So we've done that here. And then we just simplify, expand, simplify, and get into an appropriate format. All right, so I'm going to multiply the 4 across. First mistake, number 1, could be we forget to multiply that 1. Okay. Often, especially when we have even powers and if we've got a negative x, we take that negative sign through. And then because, I guess, using our index laws, that negative 1 out the front here is being raised to the power of 2, it becomes a positive 1. So whilst it might look as though the negative sign has just been omitted, in actual fact, we've squared it to make it a positive 1. So I get my 4 times x minus 2 all squared, subtract 3 from both sides to get a plus 1. All right. We can approach it the same way using my function notation. Okay. So if I start with y equals f of x, dilate by a factor of 4 from the x-axis, which means the whole function value gets multiplied by 4. I'm going to reflect about the y-axis, which makes it f of minus x. And then I'm going to translate 2 units right. So the key is to make sure we end up with an expression that clearly shows I've got a reflection and I'm shifting 2 units to the right. So we take that negative sign out and then write it as x minus 2 because we're moving to the right 2 units. And I've got my minus 3 there because we're going to subtract 3 and move everything down. So once we've done that, we can then substitute that expression into the function that we've been given to deal with. And if we do that, it might look a little bit, well, in actual fact, if we compare that to what we had previously, okay, there's the 4 times the function x plus 1, which was sort of this line here, over on the right, and then the minus 3 is because we've taken the 3 across. So hopefully you can see at this line here, it's an equivalent expression to the second last line of the first time we did it, all right? But as I said, it is nice to have both methods, but I do prefer you to use the coordinate approach. In particular, we use that a lot when we do our matrix transformations. Same thing, same set of transformations, but they're in a different order. So what impact does that have? Well, let's have a look. 2 units right, 3 units down. So we add 2 to the x value, we subtract 3 from the y value. Dilate from the x-axis by a factor of 4, which means the y coordinate gets multiplied by 4. So the whole thing gets multiplied by 4. Reflect about the y-axis, the x coordinate gets multiplied by negative 1. So the whole thing gets multiplied by negative 1. So once again, I get my x dash equal to negative x plus 2. My y dash equal to 4 times y minus 3. Again, rearrange, transpose, and we get an x equals and a y equals. Substitute those into the equations. Y dash plus 12 on 4, negative x plus 2. Again, that negative sign can come out. We square it, make it a positive 1. So again, I get my 4 times x minus 2 all squared, but this time I end up with a minus 8. So clearly a very different function, just depending upon the order that we do our transformations. Again, using the function notation up here in the top right corner, 2 units to the right, 3 units down, minus 2 minus 2 minus 3. The whole function gets multiplied by 4. So notice the 12 has become, the 3 has become a 12 now. Yeah, and then the whole of the x coordinate or x term in the function is multiplied by negative 1. So it becomes a negative x plus 2 within the function. All right, so again, substitute that information into my function. I probably could have left it as negative x plus 2, so I've got my 2 minus x in there, all squared. Again, the negative sign can come out the front. It gets squared 4 times. I've got the 4 there. So you can see how we end up with the same rule, but obviously we do a slightly different approach. Okay, so look, I'll leave it to you which method you would take, but yeah, you certainly need a knowledge of the coordinate approach because we'll use that in matrices. Off you go. So example 2, we've got a graph. We've got the graph of y equals f of x, and we've got to apply these different transformations to it. Okay, so I guess this is where it is important to be able to read the function notation. So if we just rearrange that function notation into a form that we're familiar with, I'm going to put the function first, so it's a negative function at the front. Bring the 2 out, we want the coefficient of x to be 1 always, so just rearrange so that is the case. So we'll 2 out the front, x minus 1 plus 3. So clearly we can see the transformations that have taken place there. Negative out the front, we reflect about the x-axis. 2 inside the bracket is dilate by a half from the y-axis. Negative 1 inside, we make it 1 unit right. Obviously plus 3, 3 units up. So if we sketch that graph from the original, so if we dilate and reflect first, we can see the reflection here. We just flipped everything upside down. So my asymptote is now at y plus 1, and my turning point is at negative 1 now. I'm then going to, what have I done? We're going to dilate by a half from the y. So from the y means the x values get multiplied by a half. So really the significant change is those x coordinates are now a negative a half and a half. Okay, my y values don't change, so that's all good. 1 unit right, 3 units up. So let's bring this point here at negative 1, 0. If I take it 1 unit to the right, it becomes positive 1. If I take it 3 units up, it becomes 2. So that point there becomes the point 1, 2. We don't know what the x value is. We know the asymptote moved up 3 units, so that's now at 4. So we know that that's pretty much what our graph looks like, something a bit like that. We probably could label those points there, but they're just random points, aren't they? That's where our x-intercepts ended up. Okay, so that's what our graph looks a little bit like. Example 3a, what sort of transformations have taken place? Well, if we have a look at the graph here, we can see that clearly it's been reflected because my asymptote is underneath the x-axis now, the graph itself is underneath the x-axis now. So we've got a y value is being multiplied by negative 1. And the x values, well, since the coordinates haven't changed, okay, we know the x values have changed, but they've changed by a factor as opposed to being shifted. And obviously they're half as big. So the x coordinate is half as big. So we can sort of see the point 2c has become the point 1 negative c. So what does that mean? Well, the x value has been multiplied by a half. Oh, that looks like an error there, doesn't it? Let's just check that. So the y value has been multiplied by negative 1. So that's certainly a reflection about the x-axis. The x value has been multiplied by a half, which is a dilation from the y-axis. So good thing we're checking that, isn't it? Just clarify that. That's a bit better. All right. Let's go to the next example. Okay, we can see there we've got a power function there, so it doesn't really matter what the function is. We've just got to apply the transformations to that rule. So again, you know the method I prefer, x dash y dash. So x dash y dash becomes, we reflect it in the x-axis, okay, so the y value gets affected, negative y. Dilate a half from the y-axis, so that's my x-coordinate that's being affected. 3 units to the right, add 3, 4 units down, subtract 4. All right, we know the process, x dash is now equal to half x plus 3, y dash is negative y minus 4. Transpose and get x and y equals, and then just substitute those expressions into whichever rule that we're talking about. All right, obviously if we divide by a half, we can flip it upside down and multiply by 2, don't we? So we have our negative y minus 4 equals 3 times 2 times x minus 3 all to the power of 5 on 2. Now I guess the inclination might be to bring this 2 out the front and join it with the 3, which would be 6, but we can't because 2 is being raised to the power of 5 on 2. So really that term is 2 to the power of 5 on 2 times 3. And that doesn't really simplify very nicely. All right. So rearrange, transpose, and we get our new function. Okay, y is equal to. All right, good luck.